let's try and solve this indefinite integral that involves roots here. So the guiding principle is somehow we want to get rid of it through maybe substitution, and hopefully can turn it into a polynomial, or at least turn it into a rational fraction that where both the denominator and the numerator have polynomials, which is of course much easier to deal with roots. So if we straight away let this root equal to t, maybe, will it work? Right, square both sides, equal t squared. Can we, in other words, express x in terms of t that involves nothing, involves no roots at all? So I highly doubt that, because this one, x, is a quadratic function in terms of x. So in the end, if we really going to express x in terms of t, it's still going to involve roots. Right? For example, x squared plus 2x, right? Both move to the other side, move this term to this side, right? Plus t squared minus 1 equal to 0. Solve for x, right? Yes, so it's still going to involve some roots here. Right? Square root of b squared minus 4ac. You cannot have a nice polynomial or rational fraction. So luckily, we have this Euler substitution in calculus, which says it has 3 different types for 3 different situations. So in this situation, we have the leading term whose coefficient is negative. So in that case, it says we can simply let the square root equal to x times t, plus or minus this constant, maybe minus. So if that's the case, then we square both sides, see what happens. Right? Minus x squared equal to x squared t squared minus 2xt plus 1. Right? So the ones cancel out. Right, here we can maybe cancel out x if x doesn't equal to 0. Right, got to be careful about this one. So negative 2 minus x equal to x times t squared minus 2t. All right, move this term to this side. X becomes common factor. So x t squared plus 1. Move this term to this side. 2t minus 2. X equal 2t minus 2 over t squared plus 1. So we really successfully express x in terms of a not polynomial but rational fraction in terms of t, right? But that's already good enough, right? Even not a polynomial, but rational fraction is good enough. And also, not only that, what's dx this time, right? We have to work out dx. Okay, dx. All right, denominator square. We have for differentiate top, copy down the bottom, minus copy the top, differentiate the bottom, 2t. Right, so minus 2t. Okay, this time. T squared plus 1 squared. T squared terms, what do we have? So 2t squared. T times 2t times negative 2, negative 4t squared. So negative 2t squared. What's the t term here? Plus 4t, I believe. Then plus 2 dt. Okay, now we can successfully rewrite our integral. Right? I say, first of all, what's the denominator look like? 1 plus square root of, right? So in other words, 1 plus this one, right? So 1 and negative 1 cancel out. Xt sitting at the bottom. But what's xt? What's here? Here's x. So xt should equal to xt should equal to 2t squared minus 2t over t squared plus 1. So all I need to do is to work out this one. First of all, what's dt? What's dx? Dx is this one, right? So t squared plus 1 squared negative 2t squared plus 4t plus 2. Right? What's the denominator? Like I said, denominator xt, right? 1 plus that square root. Xt is this one. T squared plus 1. 2t squared minus 2t. Right? Simply, we can cancel out this one. T squared plus 1. T squared plus 1. We're only left with one of them. And okay, let me see. 2d. Okay, like I said. So this one is gone. So at the denominator, all I have is 2t squared minus 2t. All right, so this t squared plus 1 squared, I'm only left with one of them. All right. Here, t squared plus 1. Negative 2t squared plus 4t plus 2. All right, this is what I have. So maybe I can now just cancel out the 2's at the same time. At the same time, I can just put this, multiply this, both of them sitting at the bottom. Right, 2. The 2's are gone. This becomes 2. So t squared plus 1 multiplied by this one without the 2. So t squared minus t. And this becomes 1, 2, 1. So negative plus 2t plus 1 dt. Right? And this time, maybe I can write it in this way. So copy down this one. Then I have take out the t here. Then t minus 1. Then t squared plus 1. Right? So all we have to do is to break them, split them into 3 terms. Right? So first term I have a over t, some constant, plus, right, this one, t minus 1, b over t is minus, plus t squared plus 1. Right, since it's a quadratic expression whose discriminant is less than 1, less than 0, right, b squared minus 4 is negative 4, less than 0. So we have to use c times t plus d. Right, both a, b, c, d are constant to be determined. We always have this kind of formula. So right now the thing is that how to determine. Right? I say, so this they're a common denominator. Right? When you combine them all together, so a should multiply by these 2 terms, b should multiply by these 2 terms, ct plus d should multiply by these 2 terms. Then they add up to this term. Right? Like I said, so a times this term, b times this, so bt times t squared plus 1. Then finally ct times, so t times ct plus d times t minus 1. They should add up to this one, negative t squared plus 2t plus 1. Now the question becomes, how do we determine the value of a, b, c, and d? One way is to, like I said, after finding their common denominator, we work out, right? The numerator becomes this one, must equal to this numerator, always. So one way is to work out the cubic term, compare this coefficient on this side of the cubic term with the cubic term on this side, their coefficients. And you compare the same thing for t squared term, t term, constant term, until you work out a, b, c, and d. So a slightly quicker way might be substitute t with some special values. Right? T equal to 0, t equal to 1, t equal to negative 1, then work out the value of a, b, c, and d. Right? The reason is because they always equal to each other, no matter what the t value is. Right? So I can try special value of t, like t equal to 1, for example, here. And immediately we have this term becomes 0. Also, this term also becomes 0. Right? I'm only left with this term. Right? So b times 1 times 2, 2b. This way, like I said, might be quicker than comparing the coefficients. So equal 1, negative 1 plus 2 equal to 1. 1 plus 1 equal to 2. So b equal to 1. Then another special value, t equal to 0. Yeah, let's try. So then all of a sudden, this term disappeared. Right? Also this term. Right? So this term stays. Right? This term becomes what? Negative 1 times 1, negative a. So right hand side becomes 1. Right? So a equal to negative 1. Right? So we've already worked out a and b very quickly. Now, so before I substitute another special value, why not just first replace a with negative 1 and b with 1 and simplify a little bit, right? So this time my left-hand side will become negative t minus 1, t squared plus 1, plus bt, so plus t times t squared plus 1. Then plus t times ct plus d times t minus 1 equal negative t squared plus 2t plus 1. All right, so this I say common factor t squared plus 1. I'm left with t minus t plus 1. Right, just times 1. Right, then plus t times ct plus d times t minus 1 equal negative t squared plus 2t plus 1. Right. So let's continue substitute t with special value. So t equal perhaps negative 1 this time. So 2. So negative 1 here, negative 2 there, so positive 2 up here, in front of here. 2 times ct plus d. So d minus c should equal to, so negative 1 plugging here. So still negative 1, negative 2, negative 3, plus 1, negative 2. Right, simplify a little bit. So 2 move to the other side. Negative 4. Right, cancel out the 2, so negative 2. Right? Maybe next I said t equal to 2. All right, so 5 plus so 2 minus 1 equal to 1. 1 multiplied by 2, still 2. 2 times ct, 2c plus d equal 2 plugging here. So negative 4 plus 4, 0 plus 1. Right? So this one. So move this 5 to the other side. Becomes negative 4. Right? Cancel out the 2. 2c plus d equal negative 2. Right? Everything correct? So, right, this equation 2 minus equation 1. D cancels out. 2c minus c, 3c equal 0. C equals 0. D equal negative 2. All right, so A equal negative 1, B equal 1, C equal 0, D equal negative 2. Now all we have to do is to plug A, B, C, and D into our integrals. Then the rest should be easy to solve. Right, so I can break it into 3 different integrals. First integral is negative 1 dt. T. Second is what? Plus t minus 1 dt. Third one. D is C is 0, right? 0 plus negative 2. Then t squared plus 1. Right? This is just a standard integral. So for this one, negative log absolute value of t plus log absolute value t minus 1. For this one, so negative 2, of course, arctangent of t and plus c. All right? Then we just say, okay, this log, we have this log, combine them together, do the division. Log absolute value t minus 1 over t. Right? Arctangent. Like I said, so we have to substitute t back in terms of x. All right? So in this case, t should be equal to, what is it? I think it's 1 plus square root then over x. So remember I mentioned in the beginning, when I did this substitution, Euler substitution, right, I just simplify a little bit. In the end, I just cancel out x. You can also tell from here, x is now in the denominator, which means x is not equal to 0 in this case. Right, that's our condition here. But first of all, I can say t minus 1. Right, t minus 1, we can easily work out. Then over t. Right? In the end, the x will cancel out. Right, t minus 1, top will become 1 minus x plus the square root. Right, 1 minus x plus square root. The bottom will become, like I said, so just flip this one. So So this will sit at bottom. Here, minus, not plus, minus. Right, so t minus 1 over t. Right, flip this one. X will cancel out. Minus 2 arc tangent t plus c. Right, of course, like I said, t is now over x. 1 plus 1 minus 2x minus x squared plus c. Here x does not equal to 0, right? Which means this is my antiderivative, my primitive. I say, I call this whole g f of x plus c, right? Which means f prime of x should equal to the inside 1 over 1 plus square root, right? When x is not equal to 0, right? But I'm not done yet, right? So don't start celebrating yet. Right, we have to discuss when x equal to 0, what's its antiderivative. So like I said, we cannot start celebrating yet until we find out its antiderivative when x is equal to 0. Right, so the problem here is that when you have a look at this function, let's call it f of x, right? So even though it doesn't have a definition at 0, but do we have a limit? Right, x approaches 0. Right, you have a numerator, you have 1 minus 0 plus 1. You have 2. Right? Then the denominator, you have 1 plus square root of 1. You have also 2. Right? So this is not undetermined. This is a perfectly normal standard limit. Log of 2 over 2. That's log 1. That's 0. Right? Then you have here. Right, you have 0 at the bottom, you have 1 plus square root of 1, 2 over 0. Right? So it's either positive infinity or negative infinity, depending on whether x approaches from the right-hand side or left-hand side. Right? If, let's say, x, right, okay, the limit, right, it doesn't have a limit. Let's say that the left-hand side limit. Right, so when x approach from the right-hand side of 0, you have arc tangent of positive infinity, right? That's half pi. Right, then you multiply by negative 2, you have negative pi. So we have the right-hand side limit, negative pi. So when x approaches from the left-hand side to 0, of course, remember the graph of arctangent, right? The graph of arctangent, right, is this way, right? Right, when you approach, right, negative infinity down here, so negative half pi, or all the unit circle, whatever. Right, if it's right, so half pi is positive infinity. Right, negative infinity is negative half pi. Right, so here, negative infinity, right, negative half pi times negative 2, you have positive pi. Right? So you have two different limits from the left and right. So you don't have a limit. So roughly speaking, the graph will, it's not accurate, but just a rough idea, right? Illustration. It'll look something like this. I don't know. Maybe it'll even have a restriction for x, right? Because you have a square root, right? 1 minus 2x minus x squared. It has to be positive, right? So it's like a quadratic function, right? Facing downwards, right? Whatever. Right? You have some restrictions here. Right? Cannot be great, Right? You have the left-hand side limit, right-hand side limit, negative pi. Here's positive pi. You approach from the right-hand side to 0. Maybe looks something like this. Remember, we don't have a definition at 0, right? So it's a hollow circle. When you approach from the left-hand side to 0, you're approaching pi. Maybe something look like this. And you don't have a definition here, but you do have a tendency. Maybe some restrictions for x. For example, we don't need that, we don't need this. That's the f of x, it's graph, roughly. Like I said, no limit, right? You have different limits from the two sides. So what can we do, right? Or maybe we can, shift the graph, right? This piece of graph downwards, right? Pi units. Shift the right-hand side graph upwards, also for pi units. Right? Then let them meet. Then we can redefine the function at 0 as 0. Right? Well, we can definitely do this. Right? Shift it downwards a bit. Shift this one upwards. Right? So originally they don't have a definition. It doesn't have definition at 0, but now you can redefine the function at 0 to be 0. Now this time, right, the graph it's definitely continuous, right, at point 0. Right? So we can define like this piecewise function. I say, I'll redefine g of x equal to, if x is less than 0 and greater than whatever this, then I define it as the f of x minus pi. Like I said, shifting it downwards, right, in this way. If it's x greater than 0, smaller than whatever, I say g of x should be equal to f of x plus pi, because I'm shifting it upwards. If x is equal to 0, I'm redefining it as 0. Right? Like I said, this time, right? Downwards, upwards, they redefine it as 0. Right? It's continuous everywhere, including 0. Right? So this time I can safely say that no matter x is equal to 0 or not, the antiderivative of my original should be equal to g of x. This time I can, right, finally plus c. Last but not least, we have to verify that our amended function based off of f of x, which is this one. When x is not equal to 0, it's this one. That's the antiderivative of this one. All right, amended to be this function. Right, shifting it downwards on the left-hand side by pi. Shifting the right-hand side upwards by pi. Right, meeting at 0. Continuous everywhere, including 0. But the thing is that we don't know for sure if it's derivatable at 0. We don't know. Right? Even though it may look like it's differentiable. But we don't know. Right? You cannot even look here. When x is not equal to 0, when x is equal to 0, right? Here we have 1 over 2. Right? Whose antiderivative is x over 2, but that doesn't matter. So this just means when x equal to 0, can we prove that its derivative at 0 is exactly half? Right? The thing is that we cannot straight away differentiate f of x. Right? It's only meaningful when only x is not equal to 0. right? F of x is only meaningful when x is not equal to 0. Right? So even when you differentiate it, it'll give you a function of its derivative at all the points except 0. Right? So you cannot just differentiate this one and plug x with 0 into it. Right? So instead, we have to use the first principle, right, to g of x. Right? Let's say g of h minus g of 0. Right? First principle. Right? Maybe I say h approach 0 from the right-hand side. Right? Because we don't know if it's differentiable or not. Try the right-hand side, then try the left-hand side. Find out limit, if there is a limit. Right? First principle of derivative, g of h minus g of 0 over h minus 0. But g of 0 is what? Defined to be 0. Right, so all we have to work out is this one. When h approach 0 from the right-hand side, what's its limit? Right? But for this one, we can actually use L'Hopital's rule. All right? It's because the condition is that as long as this function is defined not necessarily at 0, right? For an open interval from 0 to some point, as long as it's meaningful, and as long as it's differentiable, not necessarily at 0. Just needs to be an open interval, 0 to some point. It's differentiable. Yeah? Yes, of course. Right? Differentiable. Then we can apply L'Hopital's rule. Right? Differentiate both top and bottom. Right? But here, h is not equal to 0, just approaching 0 from the right-hand side. Right? So in this case, we can legitimately use g prime of h. We can legitimately use f prime of h. It's totally legitimate. Right? H is not equal to 0. Right? All we have to do is to replace x with h. Right? When we say f prime of x, we can say f prime of h, right? Knowing that this is already the derivative of this one when x is not 0. I just replace x with h. That's our g prime. 1 over 1 plus square root of 1 minus 2h minus h squared. Let h approach 0 from the right-hand side. Then that's 1 over 2. Right? H approach 0 from right. Then it turns out it's going to be the same result if h approaches 0 from the left-hand side also. Exactly the same result. Right. So that's how we verify that